Hi, everybody. I hope that you're all doing well. In this lecture, I want to introduce you to the concept of regression, which is an extremely important technique in pretty much all of applied statistics. And in fact, even at the highest levels of statistics, if you think about the fancy machine learning that you're hearing about, or even Chat GPT, I'm sure I'm kind of dating this video for viewers in the future, but in the last month, this has become very mainstream news, this extremely advanced AI. Fundamentally, what that is regression, as a matter of fact, which is a really cool thing. So, in this video, we're unfortunately going to learn from the perspective of understanding all that very fancy stuff, the very, very fundamentals. But at the same time, if you really did want to take this material and either become a practicing sociologist or get really into machine learning, you would want to start with exactly this kind of fundamental analysis. And indeed, the way that I teach it is cuts really to the heart of how regression works, and so you're not getting too bad of a start by beginning here. So we'll go over some key facts and a bit of intuition for the formula's origin, a little proof. Then we'll add some regression to our correlation example. Kind of do these sort of back and forth, so it's not going in a linear fashion. We'll go over some advanced regression facts. We'll talk a little bit about regression diagnostics, and then we'll wrap up. So here's where we've been so far in this class. We've gone over descriptive statistics for univariate distributions of quantitative variables. So looking at one quantitative variable at a time and then trying to sum it up with some basic techniques. We've gone over measures of the central tendencies, so the mean, median, and mode. We've gone over measures of spread and dispersion, so the quantiles, the five-number summary, both of which you can think of as sort of vector measures, or in other words, measures that come in lists, but then also scalar or single number measures such as the variance and the standard deviation, which are typically substitutes for one another. So while that is two measures, we usually use one or the other. And then the simple range, which is also a scalar or a single number. We've also been talking about how to standardize data from normal distributions specifically. That might seem like a bit of a detour now, but it'll become very useful in future weeks. We've also gone over some graphical methods. So we've talked about cumulative distribution functions, probability mass functions, and probability density functions, and box plots. And again, these things might seem a bit like detours. We've talked about them just in passing, but we'll use all of these down the road a little bit. But we're focusing now on tools for describing bivariate distributions, and we're first going to finish up our discussion of numerical techniques today by discussing not only correlation again in some review, but regression, then also graphical techniques. We've reviewed scatter plots, but today we're going to learn how to put up a regression line. And we'll see later on that all of these things come back together. So the very end of this course describes how actually the normal distribution and regression slopes in a sample have an enormous amount to do with each other, but that'll have to wait for a while. Here's a summary of our measures so far. I won't review this in too much detail, but this is basically a little cheat sheet for you. So let's talk about what regression is. So it gives a line of best fit for points on a scatter plot in the bivariate setting. It can get more complicated, but we won't discuss that in this class. The population linear regression model, in other words, what we believe to be true at the population level, is this. It is that y is equal to some intercept, beta naught, plus beta 1, our slope on the predictor, times x, the predictor, plus u, where u is an error term, so it's just the difference between an actual person's value on the outcome y and then the predicted or deterministic component of the regression analysis, this here, the intercept plus the slope times the predictor. And these betas are different than the source textbook that we use in this class, which is Mornotz and Fligner. But this is common at higher levels, and so I choose to use this notation just because it's what I'm used to using. And you'll see it very often outside of this class. So we're not going to use y equal to mx plus b, in part because we would be introducing an error term, and that term would change the regression equation from what you're used to anyways. But fundamentally, it is a line. The regression slope beta 1, in fact, has an interpretation that is very, very similar to how you interpreted lines in your high school algebra courses. So it gives basically when you change x by 1 unit, it gives the amount that you expect the outcome to change by. And in a sample, this has a really nice, easy relationship to the correlation coefficient. So how do we come up with this beta 1? Well, we multiply r, the sample correlation coefficient, by the ratio of standard deviations, where we have the outcome on the top and the predictor on the bottom. And if you happen to want to do the inverse regression, so regress x on y, you would just flip that ratio as well. Y and X here are positional, so they refer to which is the outcome, which is the predictor. But you don't have to make, you could do the regression in reverse if you like. So that's how we do that. And that's a pretty cool fact, in fact. And we'll see later on why that's true. So the goodness of fit of a regression, in other words, how much, basically how close our fit is, or in other words, I want to put it kind of exactly here, but I'm trying to avoid getting ahead of myself. Let's just say it's basically a generic sense of how good of a fit our model is to the data is given by the correlation coefficient squared in this bivariate setting. And there's many other ways to express that goodness of fit that happen to be identical to it, but that'll come later in the video. So the sample intercept is given by beta naught with a hat on it equal to y bar, the sample mean of y, minus beta 1 with the hat on it times x bar. Now the hats mean that the quantities are estimated, so just like the bars and the x's for the means indicate that that quantity is an estimate from the sample, it's not a population quantity. The hats are true just generally, and in fact, hats are a little bit more common notation. These bar notations are sort of the exception to the rule, even though we meet them first. Among other things, this implies that x bar, y bar is on the line. You can see that by plugging in x bar here, and then noting that beta naught is y bar minus beta 1 hat times x bar, so the beta 1 hat x bar terms cancel out. We have y bar is equal to y. And we actually don't need to worry about that error term in that equation. In fact, it would be a residual term for the sample, but also this is a model that basically gives us not the predictions, but the actual location of all the points. That's a subtle point. If that seemed a little bit loose, don't worry about it for now. So this method is known as ordinary least squares, and this method, the reason that it, the criterion that it follows, the reason that this way of estimating the regression slope isn't totally arbitrary, well, the criterion that it follows is that it minimizes the sum of squared residuals, or deviations from the sample regression line. By the way, in the way that we estimate it, which is the very standard way, the sum and mean of those residuals is equal to 0. We'll see a little proof of that later on, and there's actually a variety of ways of stating that criterion. You can think about it as it makes the residual vector as short as possible, and there's a linear algebra connection between the sum of squared residuals and the length of, or the squared length to be most exact, of a vector. You could also think about it like it makes the residuals and the predictor have no correlation, or it makes their vector representations orthogonal. These are all the same thing. There's many regression caveats, by the way, and caveat is just a fancy schmancy Latin word for thing to watch out for. I think it literally means danger. My Catholic school teachers are not happy with me right now for not remembering that, despite using that word maybe too often, but it means watch out. So there's a lot of things you got to be careful about when it comes to regression. Okay, so let's pick up with our toy example that we were using last time, which involved commute and earnings data that I just made up for convenience. Last time we found that this was the correlation coefficient. We won't re-find it again today by hand or that often in the future. Remember that this is a units-free measure of association between two variables, but we may want to use it to actually tell us what the concrete relationship is between two variables, one of which we consider to be the predictor. And that procedure is known as regression. So this is what it looks like. Here I used commute in miles as the predictor and earnings in thousands of dollars as the outcome. And this is the regression equation here. I made this in Stata. It doesn't automatically print this information for you. You have to do a little bit of coding to get that to happen, but you can do it using the code in the comments. I'll just briefly show that in case people want to know. So I always paste it down here. You'll need to get the data. You'll need to make sure you have a couple of packages installed, basically. But other than that, it's not too hard. Understanding the details might be a little difficult, but you can at least swap in stuff and see that it works in your computer. Okay, so this is the equation. So what this tells us is that basically for a mile increase in one's commute distance, so the units here are in miles, so we say let's increase this x by 1. The outcome goes up by 0.47. This is in thousands of dollars, and by the way, I'm not just being annoying here. A lot of times the units are not just one of the things, so you got to be careful about that. Regression is sensitive to units, unlike correlation. That's an important point. So what that tells us is that the person's earnings increase by about 0.47 times 1,000, or about $500. The regression intercept is basically the value of the equation when this is equal to 0. And that tells us that a 0-mile commute is associated with an income of $32,670 because that's all that's left over when we plug in a 0 here, and this goes away. And so that is the basic interpretation of our regression equation. You can see here that this number 32.67 is also where this line would cross the y-axis when x is equal to 0. And you could also spot check if you wanted by picking 2 points that appear on this line that the slope indeed appears to be about 0.47. So all that stuff is just kind of regular equations of lines from our high school geometry and algebra, but we'll see that we need to do a little bit of additional work to come up with the actual equations for these things. And incidentally, this here, really, this y should really have a hat on it to indicate that this is the predicted y. It's not the actual y, but I'm just writing this kind of loosely here because usually from context it's obvious what we're trying to say. The actual y's need a residual term here in order to indicate that all these points, for instance, are pretty far from the actual line. In a more realistic example, most of the points might be fairly close to the line, but few of them will lie on the line, so that's something worth noting. Okay, so let's try to get that slope by hand, and here's how we would do it. Recall that the coefficient beta 1, which is the slope, is given by the correlation coefficient multiplied by the ratio of standard deviations, and again, the hat just means it's the sample estimate. There is a population analog to this that we won't be able to actually observe in reality. So our standard deviations in the sample that we found last time are 13.69 for commute and 21.68 for earnings. So we can go ahead and plug that information in, and what we get is 0.47 rounded. So 0.295, we found that from before, but it was also pasted into the figure here. So hopefully you were able to find that. And that's what we get here from the actual program here, which is Stata. So we can also find the regression intercept in the same way. And so again, what that means, what this tells us here, this is the intercept, beta naught, and then we estimate it. So we put a hat on it. We take the sample mean of y, and that's given here. So that's 42 for earnings. And then we subtract from that beta 1 times x bar. X bar here is 20. And then beta 1 we found before was 0.47. And when we plug all that in, and I used a more exact expression from Stata here, but we get 32.66. So this matches Stata with a tiny bit of rounding error. And again, we went over the interpretation from before. I won't belabor the point. So let's interpret the line one more time now that we've gone over this. For a mile increase in one's commute distance, we expect someone's earnings to increase by about $500. And a 0-mile commute is associated with, again, you can see here, if we set x equal to 0, an income of about $32,000. So how good of a fit is our regression line? Let's be a little more exact here. So we calculated this in a bivariate setting that should be calculate by simply squaring the correlation coefficient. And I'll show some intuition later on for why that's true. But it's kind of a surprising fact at first. The way we would interpret it is this. So first of all, we calculate it, and then we say about 9% of variance in the outcome of y is explained by variation or variance, but let's change that to variance here in x. So variance is the more exact term, and it literally refers to the square of the standard deviation, but sometimes you'll see it printed as variation, which is just a more generic term that doesn't necessarily mean variance. So that's how we would interpret this here. Let's look at a little bit more of a realistic example before we go ahead and say where some of this stuff comes from. So try in your mind to figure out the way you would interpret this example where you've got respondent's education on the y and father's education on the x. This is drawn from the GSS 2018, and here's your regression equation. So see if you can come up with all the stuff you would want to come up with. So I'll go ahead and interpret this. For every year increase in father's education, the respondent's education is predicted to increase by about a third of a year, and I'm rounding up a little bit here, but I think that's because it's nice to put this in familiar terms. The intercept in this case is, well, first of all, the intercept is not always guaranteed to be meaningful in regression. We include it for a variety of reasons, one of which is that it makes it so that the residuals have a mean and also a sum of 0, which is a fact from linear algebra that you don't necessarily need to understand to watch this video. And in fact, I won't really give a proof here. There's a proof in the appendix. But the intercept in this case does happen to also be meaningful because the father could have 0 years of education. That wasn't certainly impossible for people answering this in 2018 whose fathers may have been born and raised in places where legal minimums on education weren't really strictly legally enforced. It's completely plausible that someone could have 0 years of formal education, although we probably would expect to see not relatively that many. So how do we interpret the fit of the line here? And you can see visually that it's not that great of a fit. There's clearly a overall relationship, but we would say that variance in father's education explains only about a 17%. Only explains about 17% of variance in respondents' education. And you can see that the fit of the line is, generally speaking, quite a bit better as for a variety of reasons, one of which is simply mathematical. Once you get, to a point where, okay, your dad's got 12 years of education, um, and you have a maximum just based on how this was recorded of 20, because it's very unlikely that you're going to get a whole heck of a lot fewer than, say, 12 years of education as the respondent once your dad does. And you can't get too much more than 20 because you're top censored here and you just have to say 20, even if you've been in grad school for a long time, which I wouldn't know anything about. Then you can see that that actually almost forces a good fit of the slope here, or the regression equation, I should say. But in this case, down here at the kind of bottom end of the distribution, fathers actually seem to have a relatively loose relationship to their children in terms of the education they receive. And you can think about a variety of reasons for that, one of which would be that children, generally speaking, in the last century have been born into situations where there is more pressure on them to get a formal education than there was on their fathers. And so that might mean that there is a whole variety of other influences on that outcome. So, not too surprising to see that the regression equation doesn't fit as well here. There's a formal term for this change in the fit that becomes very important at higher levels, known as heteroskedasticity, which is a big fancy term that means uneven spread. And we'll come back and talk about that very briefly later on. Here's another example of a regression equation. I'll go ahead and let you interpret this. Again, I'm going to kind of skip ahead here because this part can be a little bit tedious. So, hopefully this is kind of autopilot, and then we'll get down to the really interesting stuff, which is why these things are true. But the way we would interpret this regression equation is as follows. For every increase in someone's work quality score on this data taken from the MIDAS biomarker project, your stress score is predicted to decrease by 0.62 units. Now, these units are fairly artificial. I just happened to find this data, and it had a PI on the project from the place I'm teaching currently, which is UW-Madison, so I thought it might be fun to use. But I don't know a lot about this data set, and I, in particular, don't know a whole lot about how these work scores and stress scores were constructed. And that's a lesson, which is that if you're going to run regression, sometimes people act like having these mathematical tools just gives them an automatic insight into everything that could be known about a particular data set. But I want to kind of ward you off from that interpretation. That actually is not true at all. So we can interpret this mathematically without knowing too much about how these things were measured, but you would want to go and check that out if you were actually interested in this analysis. So how good is the fit? Well, we can see visually that it's not that great of a fit. There's a big cloud of points here. And again, that could be because there is no relationship between these variables, or it could be because maybe they were measured very noisily. It's not easy to measure someone's work quality or their stress for that matter. So this is what the data look like, for whatever they are. And here, the intercept is not especially meaningful, actually. Um, did I put something on that? I didn't, sorry. So I would say here it's not, because evidently it was impossible in the actual observed data to have a good work score of 0. So we may not want to put too much meat on that. Also, the fit of the data to the regression model is very poor. So we would say here, if we square this quantity here, you would see that you're going to get a number that's basically like 0.064. And so rounding what that means, or 0.0064, pardon me. So rounding what that means is that basically we're going to get, variance explained of about 1%, which is a very low quality fit, which you can also see visually. So let's do a little bit of conceptual practice before I show you where some of these formulae come from. And I thought maybe a really interesting form of conceptual practice would be to say, why is it called regression? It's kind of an unappealing term, and it doesn't really seem immediately to have much to do with what we're actually doing, which is trying to fit a line to minimize the distance of points from the line itself on a scatter plot. So it comes from Galton, who is a bit of an unsavory figure, although a very interesting guy also, and responsible for a lot of the techniques that we use. Actually, the paper where he published this material on regression analysis also includes things about principal components analysis. It includes some interesting material on bivariate normal distributions. It's a paper where he's fumbling around and doing a lot of stuff in kind of a clunky way, but also doing a ton of stuff in a really kind of remarkably prescient way. But he was also a creep, I feel compelled to say. And I say that in part because it's relevant. He was super interested in heredity. And you can kind of imagine where that goes when I say he was an unsavory figure. But this is a pretty benign example. He at one point studied the relationship of children's heights to their parents' heights. And he found this interesting phenomenon that gives us the name of the term today. So, what Galton found was that tall parents tended to have tall children. Okay, pretty obvious. But children were generally closer to the mean for their cohort than parents were to their cohort's mean. In other words, children were, like setting aside the fact that there were different distributions for the two, like children are generally taller than their parents, at least for like a long stretch of history, including when Galton was looking. But basically standardizing the data and then looking and seeing, okay, are the kids of tall parents generally, as far from their mean in terms of their standard deviation as the parents are? And the answer was no. So generally speaking, people's heights regress towards the mean or regress towards mediocrity, as Galton would have put it. And so you may want to consider, and you can see an example of that here, why that was the case. And you might wonder whether or not that was a biological phenomenon or maybe a social phenomenon. And you can see here, this is kind of also an interesting way of representing joint density. So we've seen before that scatter plots oftentimes look pretty dotty when we have fairly discrete data, and Galton was measuring in inches. The British Empire at that point hadn't switched over to the metric system, or maybe they had. I'm actually not an expert on that. He was still using inches as a Brit anyways. So measuring people, without a whole lot of precision here, and it looks like he was probably doing the half inch or something like that, but maybe not too much more precise than that. So relatively discrete measurements. And so what he did, rather than using a contour plot or a jitter, both of which would have been prohibitive by hand, he was just putting in numbers into the table. So where you see 14, that represents 14 observations stacked at that point, and so on. So that's a really interesting alternative approach. I think I showed in the footnotes. If not, I'll post it sometime. I one time recently, in playing around a little bit with Python, showed how to recreate a scatter plot like this. It's a little bit tough. So the answer to the question, by the way, the actual substantial question, not the coding question, is that this is a statistical phenomenon, or at least it's both, and I'll explain how it's both. So let's pull up the figure here. I just want to have that up. So if two variables are imperfectly correlated, and they almost always are, just as a rule of thumb, that means the absolute value of the correlation coefficient is less than 1. So then think about our regression equation. If our slope is r times the standard deviation of y over the standard deviation of x, that means that increasing x by one standard deviation is going to cancel out these here. Then the predicted increase is r times the standard deviation of y. Finally, if you think that r is less than, let's just make it a positive relationship for simplicity. So r is less than 1, that means the predicted increase, is less than one standard deviation. So what that means is that, generally speaking, if your predictor increases by a full standard deviation, the outcome generally increases by less than a full standard deviation, although possibly quite a lot. So what that means is that this is a statistical phenomenon. In other words, just by the laws of how the regression slope is written, when a parent's height increases, so you go from one parent who is the mean height to another parent who is one standard deviation above the mean, then when you use the regression equation to predict what will happen to the child's height, it's going to be r times the standard deviation of the child's height. And again, because r is almost certainly going to be less than 1, that means that the child's height is predicted to increase by less than a full standard deviation. The reason that that's also a biological phenomenon, by the way, would just be down to the fact that children's height and parents' height is going to be imperfectly correlated for reasons that are biological in essence. Among other things, you could think about the fact that height, for instance, has some really strong social determinants. So it's generally the case that even though height seems like a classic genetic phenomenon, people that are from societies that have relatively high levels of development in the economic sense, generally speaking, have taller people. So let's finally look at what regression does conceptually. And I want to pull up this picture first, ignore the text on the left for a moment. So if we're looking in variable space, which is the space where our predictor is on the x and our outcome is on the y, again, there is an alternative that I'll mention soon, we have the following picture. So just imagine here for a second that we've got a scatter plot. Ignore all this other stuff. So we have here a point, and this point is defined by the kind of like joint occurrence of some value of x and some value of y. And you can think about the overall variation in y as being fundamentally this deviation, except squared and then summed and then divided by n minus 1, and that gives you the variance. And if you take the root of it, you get the standard deviation. But fundamentally, what's going on is we have at the heart of that thing a deviation, and then it's square, and then it's summing. And so this total sum of squares is fundamentally the quantity that we're talking about when we talk about variation in some variable, and then dividing by n minus 1 and then taking the root of it are basically, they're not exactly scaling factors because the root is not a traditional scaling factor, it's a nonlinear operation, but we're basically just transforming it, the kind of basic quantity here. So note that we can also, if we plop a regression line here and then plop the mean of the y's here, we can also think about, okay, well, this is a way that we can partition the variation in the outcome into two things. One is the residuals, which is a point I've already, or a term I've already mentioned, which is super important to know. It's the difference between a point yi at some value of x and y hat I, or in other words, the prediction for some given value of x. And so that here is represented by the distance of the point y from the actual regression line. We can partition all that variation, so the variation over here, into that residual, and then the remaining distance, which is the point, the distance of the regression prediction there at that point from the mean. So notice again, if you look at this carefully, you've got this overall variation, which is points from the mean, and then that distance can always be decomposed into two components, the distance of the point from the regression line and the distance of the regression line from the mean. And you can think about that as basically giving you a way to think about how much better the regression line does than just a simple mean at predicting the outcome. And so if we write down that residual, and so we say yi minus y hat I, and then square it, that gives us another kind of standard deviation, which goes by many names. You can think about it, the way I like to think about it, as the conditional standard deviation. And it's got a bunch of names, though. For instance, here, this is just the sum of the things, and you can see this textbook actually refers to it as the sum of squared errors, which is a highly unfortunate term because errors and residuals are not the same thing. Residuals are estimated errors. Errors are the distance of the points from the actual regression function. Remember that we don't even know the regression function, we just know pardon me, an estimated version of it from the sample. But this is the quantity. The quantity is what matters. And then we've also got the model sum of squares here, which is this quantity. And this is finally another type of basically variance or standard deviation. It's this variation of the predictions around the mean here. And so you can see that these things all have to add up. And that's basically a version of the Pythagorean theorem, and that's maybe even truer than you might realize. I'll show it on the next slide. But the important point here is that this ratio, this model sum of squares to total sum of squares, is also equal to r squared, which is a pretty cool fact. And there's a couple of different ways to see that, but I just want you for now to know that these things happen to be the same, and there's a really nice geometric proof that I'll show in a second, but that proof basically just kind of flips the geometry on its head in a certain way. We've seen it once before in this series, and my YouTube page has a lot of videos that go into detail on this. It's a little hard to see at this level without going into that, But I just want you to kind of get that sense because I think this material is understandable at this level. So what regression is doing is basically taking this overall variation and then trying to reduce that variation, right? So trying to basically say, can we use X to somehow give us a better prediction of Y than, say, just the mean, which is the most basic kind of prediction. And we can think about what regression does is basically taking that overall variance that we began with and then chopping some of it out by plopping down a regression line. And we can actually quantify basically how much variation is left over, is unexplained, and how much variation is sort of chopped out, if you like. And that's a way to kind of think about the regression equation. So let's talk a little bit about how we get those formulae. And for the class for which I'm producing these videos, this isn't strictly necessary by any means, but I thought I would include it because it might be a point of interest. And it's actually not too hard to understand, so I hope that you give this a shot, even though it's not strictly necessary. So here's how we get those formulae. First, it turns out that we can split up regression into two independent operations. One, finding the intercept, and two, finding the regression slope. The slope part happens in a space of centered variables. So the intercept part happens in a space that is orthogonal to that, to use the linear algebra term. That term may not make sense to most people watching this directly, but you can just know it means that they're independent. We can actually state our goal in three different ways. The first one, make the covariance of residuals and the predictors zero, and in this case the predictor just is one item. Two, we can make the residual vector perpendicular or orthogonal to the predictor vector. And then three, finally, we can find beta 1 to minimize the sum of squared residuals. In other words, we're going to find beta 1, which is the argmin, the value that minimizes this function here. And sorry about that. My trackpad is, well, it's really Google Slides' fault. It's just extremely sensitive to the trackpad. So first, let's look at this proof here. And we'll actually just look at this first one. These all come to the same thing, by the way, and I'll mention two along the way. So here we've got centered variables. So we're first going to say we want the covariance of x and u. And I'm using u to denote the residuals because using r is more than likely going to cause confusion unless you're paying very close attention, because r also means the sample correlation coefficient. Pardon me. So we're going to say that we want this to be equal to 0. And this also means that the correlation coefficient between them will be 0. But that, because it divides by a scaling factor, but is otherwise just the covariance, isn't really necessary. This is a common situation that you'll see covariance used in because we're oftentimes in proofs interested in making the correlation between two things 0. And because the correlation can't be 0 unless the covariance is 0, because the correlation is just the covariance divided by some things, that means that it's important to use the covariance. So we'll do that here as is standard. Now, note that in this situation, because we have centered variables, that means that the x here, the mean is 0. And the residuals here, they are 0 as well. And the residuals also, by the way, can be written out in this fashion: yi minus xi times beta 1. Now what we can do is distribute this. We can ignore these zeros, by the way. We can just omit them, but I just want to show that we are using the standard covariance formula, pardon me. And then when we do all that, we get the following. So we distribute this xi here to this yi, then this becomes 0, then this gets distributed here, and we can just either distribute this or just accept that it's 0, rather than do any kind of fancier expansion. So we get basically the following. We get xi times yi minus, and then we can split up sums here, which is just a kind of intuitive property of summation operators, into xi times beta 1 here. Then our next step is to just simply move this term over, and we get the following here. And then finally, what we do is we can factor out this beta 1, because that's, again, a property of summation operators. So we'll just sum up all these xi's. They're each multiplied by a beta. That means that we can just pull out the beta. And then what we can do at the very end is just do a little bit of division. And we get this quantity here, which is cool, although it might seem a little bit like weird because it's not anything that we know how to do much with. But I want to show you this kind of cool fact. If the variables are centered, what that means then is that we are taking these, like, so this xi here is technically xi minus its mean, and this yi here is technically yi minus its mean. And so we have xi minus mean times yi minus mean, and that's the covariance numerator. And then in the denominator here, we've got, and we could imagine putting an n minus 1 up here, by the way. And then in the denominator here, this is not xi times xi alone. It's actually xi minus its mean times xi minus its mean, or xi minus its mean squared. And you'll remember that that is the numerator of the variance formula. And again, then if we just imagine putting an n minus 1 in the denominator of the numerator, so to speak, and an n minus 1 in the denominator of the denominator, then what this would be is the covariance over the variance. And so we can just omit those things here. And then finally, note that the covariance of x and y over the variance of x can be rewritten as the covariance of x and y over the standard deviation of x times the standard deviation of y, that's the correlation coefficient, times the standard deviation of y over the standard deviation of x. The standard deviations of y is canceled, the standard deviation of x squared then becomes the variance, and so these formulae are equivalent, and that's a really simple 6-line proof of how we come up with the bivariate regression slope formula. By the way, step 3 here, written as a dot product, so if you dot xi, or you dot, sorry, x and y as vectors, and then, sorry, that should say step 2. If you basically dot x and the residual term here, that means that those are also orthogonal. That's just the definition of orthogonality, is that two variables, or two vectors, sorry, have a dot product that's equal to 0. So really not too hard of a proof, and I suppose maybe the difficulty is really just in understanding what exactly is going on here, and I'll give a little bit of an intuition for that on the next page. So this is a nice way to complement that proof, because here we're looking at regression from a really different perspective. We're looking at it in subject space, and remember that in subject space, the axes that are kind of implicit here, but you can imagine an axis going here and then here, the axes don't actually refer to variables, they refer to people. And so what that means is that if you are thinking about vectors like these that you see in the space representing these variables, well, here we're in two-dimensional space. And so this y here has coordinates y1 and y2. y1 would be person 1 score on y, y2 would be person 2 score on y. Then x would be formed by taking person 1 score on x, and that's the first coordinate, and person 2 score on x, and that's the second coordinate. So this is just a different way of representing what is basically a scatter plot. This is an analogous operation to a scatter plot, except it just gets constructed in a really different way, although it's very cool. By the way, these figures are from Thomas Wicken's Geometry of Multivariate Statistics books, which is probably my favorite book about math and one of my favorite books ever, actually. So this shows us what's happening with regression. You might remember from the last video in this series that I showed you that correlation can be understood as the cosine of the angle between these two vectors, but you might remember that last time the two vectors did not have to have the same length or anything like that. So like in this picture here, you see x and y, or in this picture here, you see y, and then these two x's here. This is multiple regression. We won't get to that in this course. And what it means for them to have these different lengths here is also that their variances are different. They're scaled differently, in other words. And one way to think about that is if you think about, well, what's the length of a vector in an arbitrary number of dimensions? The squared length, anyways, is actually just the Pythagorean theorem generalized. It's the first component squared plus the second component squared plus the da-da-da up to the nth component squared. And if you have centered vectors, what that means is that in terms of the original variable, that's the first component minus the mean squared plus the second component minus the mean squared. And a really cool fact is that that's just the numerator of the variance. So what we're saying here is these vectors' lengths are directly parallel or directly proportional to the variance of the original variables. So that's a neat fact, and that's what this means here. So correlation does not require us to do anything other than just kind of look at the closeness of the things. Pardon me. But you may want to note that when we do regression, what we're trying to do is figure out how far do I have to travel in the direction of the x vector to get it as close as possible to the y vector. So this is another way of thinking about what regression does. We have these two variables, and we want to figure out by what factor do I scale the predictor so that we get the predictor as close as possible to the outcome? How do we use the predictor to basically come up with good estimates of the outcome? And so one way to think about what's going on there is we want to make the distance between the predictor and the outcome as small as possible. And so what we want to do is scale the predictor until it gets to the point where it is orthogonal to the outcome. And this vector that connects the two is here denoted with E, which is unfortunate because that is meant to stand for error. It's really the residual, but again, the notation here is kind of hellish because there's really no great choice. E would be wrong for the reason that it's not residual, or not errors, it's residuals. R is wrong because it's not the correlation coefficient. U is just not as common of a term. It stands for unobserved. But anyways, Wickens uses E. But this kind of shows you a way to visualize what was going on in that last slide, because note that this is a way of making again, this is the sum of squared residuals, right? Because the length of the thing is the sum of squares. So we're trying to minimize the sum of squared residuals. And what that also means is that if we think about, okay, the angular closeness or the cosine thereof is the correlation, that also means that the residuals and the predictor have zero correlation or covariance as well. And that also means that they're perpendicular or orthogonal. So we can see that those three criteria actually end up all meaning the exact same thing. And one way to think about why this residual here is also as small as possible, meaning that its squared length is as small as possible, or in other words, the sum of squared residuals is as small as possible. Note that if you drew a line here, or drew a line here, or drew a line here, etc., those would all be lines that are the hypotenuse of a triangle with this as one of the non-hypotenuse legs. So by definition, this would be smaller than this here and this here by the Pythagorean theorem. So the only way to ensure that this is as small as possible is to do an orthogonal projection just like this, because that ensures that all other possible projections are the hypotenuses of triangles, making the residual vector the smaller leg. So that's a pretty cool fact, and that's really what's going on. Note that this also gives us a nice sense for why the model sum of squares over the total sum of squares is equal to the correlation coefficient squared. So let me explain that really quickly. I'm going to say this out loud, but then I'll pull up the explanation later. So if this cosine of this angle here is equal to the correlation coefficient, that's true in general, and that's true even when you don't have a right triangle. So for instance, if you just look at the original x and y here, that's obviously not a right triangle, it's an obtuse triangle. So, but we still know that by the law of cosines, that is that angle here between them, the cosine of them, is equal to the correlation coefficient. That's just how the law of cosines works out. But notice that when we do regression, we're extending this x here all the way out so that it is a scalar of itself, or a scalar multiple of itself, I should say, and it's orthogonal to basically this residual vector here. So we project y down into the space of x, and then we extend x all the way out. And the factor by which we extend x is the regression slope, although in this context it's not a slope as much as just a scaling factor. And that gives us our predictions, y hat. Note also that now this is a right triangle, right? So what that means is that in this case, correlation coefficient can also, or the cosine, pardon me, can also be found by taking the adjacent here over the hypotenuse. And the adjacent is y hat, or in other words, the predictions, and then we've got the hypotenuse here, which is just the outcome. So if we square those two things, so let's say we square this length here, what that is just going to be the sum of squares of the predictions. And in this centered space here, because those have mean 0, that means that that's also the variation of the predictions around the mean, which is 0. So it's the model sum of squares. And then the outcome here is the variation of the points around their mean. Again, it's centered, so that's the variation around 0. So it's just their squared length as well. So the ratio of this squared length to this squared length is equal to the correlation coefficient squared, because that's equal to the cosine squared. And so that tells us that the model sum of squares over the total sum of squares is also equal to the correlation coefficient squared. You may wonder why we use this squaring as a measure, and that also goes down to the Pythagorean theorem. And the reason is this. It's because a squared plus b squared is equal to c squared. It's not true that a plus b equals c. In fact, that's false, and that's a very kind of common early misunderstanding when people learn geometry. So it's not true for a right triangle that a plus b equals c. That's false generally. But a squared plus b squared is equal to c squared. So the reason that we use these squared lengths here is very simple. This lets us say that we have all sources of variation accounted for because this squared here plus this squared here, so this length here, has to equal this squared here. This is just an alternative perspective on the slide that we saw from a little bit ago where I explained that it was called the Pythagorean theorem of regression, but it wasn't obvious from that picture. So that's why we use the squared lengths. It's because we can say, okay, this is one of only two components that have to add up to give the total variation. So that's explained here in writing. I want to go over some key caveats about regression lines. The first of them is that order matters, unlike with correlation. So regressing y on x is not more statistically valid than regressing x on y, but it gives different results because the ratio of standard deviations is not generally the same. We can use theoretical expectations to decide the order if it's relevant. Association does not imply causation. That goes without saying. Don't make nonsensical extrapolations. Again, kind of goes without saying, but we'll see some examples. The regression line may lack practical meaning for regions of x, and regression also involves R and thus the mean, so it's not robust. They both involve deviations, so large deviations from the mean. That could be data entry errors, or could be cases where someone's included in your data set, but you really don't think that they're from the same fundamental population as the other people. That's going to gunk up your regression analysis. So you do want to watch out for those influential points, and all the correlation caveats from last time apply as well. So here's a simple illustration of caveat 1, order matters in regression. So regressing y on x, as we do here, is not the same thing as regressing x on y. And I probably should have said variable p and q and p, because x-axis is always x, y-axis is always y, at least in the variable space presentation, but what I mean is the variable that is x here could be y here, and it's not the same thing. Association is not causation. This is a slide, one of the few cases where I tell a silly little joke in class, but yeah, Nick Cage, as harrowing of an actor and as comic tragic as a personality as he is, he's probably not causing the increase in drowning deaths, but you never know. I want you to note here somewhat seriously that this actually does have a high correlation coefficient here. Another thing that the person who made this, I actually don't remember who it is. I think Tyler or something. It's in the notes. He isn't printing the sample sizes here, but yeah, this is a relatively small number of observations because note that this is basically, even though there's very many drownings, this is drownings per year and Cage films per year. So we only have a few observations, 1, 2, 3, 4, 5, 6, 7, 8, 9 here, maybe 10. 10, 11. So what that means is it's an extremely small sample size, so we can't draw too many conclusions. Be careful with extrapolation. So note here that there's a pretty clear problem here. There's actually a couple that persists well after the nonsensical intercept. So the intercept would be nonsensical. It's not even shown. But even well beyond the intercept, notice that you can have a situation where your standing height, and this is for adults, if I'm not mistaken, I put it in the footnotes. Anyways, your standing height below a certain point from this regression analysis predicts you to have zero weight, even though that's not possible. Sorry, I think this actually includes children. And the point is that the relationship between your height and your weight is super linear for smaller heights and weights. And basically what that means is that kids are growing and they kind of grow proportionally. And then you can see here, this is kind of a sad story, but at least in contemporary American society, these data are drawn from NHANES, or the National Health and Nutrition Examination Survey of 2017 to 18. You get to a certain height, you stop getting taller, but people tend to get heavier. So even though there's a pretty strong relationship here between height and weight, that relationship tends to dissipate as you get a little bit older. Note that doesn't mean that there's no such thing as, say, childhood obesity, because there are some kids who are taller or a certain height, but then they're heavier for that height. But it means that even if you are very heavy set as a child, and I don't mean to cause anyone to feel bad about that, I was actually an extremely heavy set child myself. But what it means is that even though you may be overweight, you're getting heavier as you get taller. And so the relationship is fairly linear here, whereas adults who are, by conventional standards, fairly overweight aren't necessarily any taller than they were, a couple of years ago or something like that. So the relationship disappears, or it gets really, really loose. If you kind of think about the relationship here, it's probably, still positive, but closer to zero. Be careful with influential points, by the way. So here, I just added a point to our toy data set, the commute and earnings data set, and note that with this small number of observations, I'm able to easily change the regression slope by just adding someone at x equal to 70. So I add this person here that's not present in the data set here, and I can change the entire direction of the slope. So you really want to be careful, pardon me, with that situation. Here's a more realistic example. Note that influence is tough to pin down exactly. So commonly used criterion is that points that have high leverage or a strong influence on the line also have oftentimes enough high residuals, and those are going to be influential points. So points that strongly shape the regression line and are kind of unusual are going to be ones that you want to watch out for. Influence is an even broader concept, though, and we don't need to get super exact about it in the way that our textbook does. I wanted to show more, importantly, just the kind of practical, what this looks like practically here. So you can see this is a data set from the CPS 2019, and we had people that could work these impossible hours, so 100 hours or more. And I showed two regression lines here. I first showed them in a different shape and color. So I showed them in red and diamond shaped here, or just squares on their sides. And then I showed, how did I do this? I did, these kind of thicker black lines here, or the dot dash lines with those people removed. And then I did the regular dash line with those people included. Note that the relationship actually gets stronger because these people are working tons and tons of hours, but not necessarily earning a whole lot more commensurate with that, probably because they're data entry errors. So we just remove them here. Here's a map of basically those people using this influence versus residuals plot. And you can see that the people that score highly on leverage and large residual, once you normalize it and square it, these are people that worked 198 hours a week. So they're people up here. So these 2 points are extremely influential. They're actually dragging the regression slope down. And so we omit them, and the regression slope looks, well, we shouldn't judge it by the results. We just know that it's going to be better. I wanted to also mention some advanced facts about regression lines. Advanced kind of facts and caveats about regression lines. So the first of these is that regression is subject to at least 2 sources of uncertainty. We usually have sample data, and we usually want to know about the population. In this class, we'll cover that at length. That's part 2. But even if we know the population information, the regression slope still almost never fully describes the variation in the outcome, which is why there is that population level error term. And so that means that, regression is always, in a sense, in fact, it's the whole point of regression, a way of kind of compressing information and fudging a little bit to say big things about data while also omitting certain details that might be, somewhat inconvenient. Regression basically gives us a good guess about the outcome at each level of X. And I just said all this out loud. And again, we actually have to estimate those errors. We call the estimates residuals, but we'll come back to those later on. A key step in one way, and we saw this before, of deriving our 2 key formulae for bivariate regression, these are the 2 key formulae, is the assumption that the population error term and the variable have 0 correlation. I meant to update this. This is actually not in the appendix. It's now in part in the main slides. But what that means is that our sample regression estimates literally force this to be true. So these formulae are consequences of this assumption that the population error term and the variable have 0 correlation. So this has to be true in the sample. But the true error term for our model could be related to our predictor if we are omitting relevant variables from the model. And this is actually almost inevitable with simple bivariate regression. but we'll tolerate that in this course. So let's look at an example of what that might mean or what that might look like. So let's say we have a model where we have income regressed on education. And this is the kind of model that we can estimate in our class. And what that would mean is that we would go to Stata, we would pull up some data, and we would say regress income on education. And the results that we get from that are going to, in a way, or in one way of thinking about it, are derived from the assumption that the residuals and the predictor, the errors in the predictor are unrelated. So we force the residuals and the predictor to be unrelated. We make that residual vector literally orthogonal to the predictor. But it could be the case that in reality, the predictor and the residuals or the errors are related. When would that be true? Well, let's think about a possible third variable, such as parental socioeconomic status. So, in that simple bivariate model, we are asserting that that's basically just random noise. So that has no independent effect on income, or more realistically, and this also doesn't make a huge difference, its effect is expressed fully through education. So in other words, it doesn't have any independent influence on basically on income. But there could be all kinds of reasons to believe that that's not the case, and that it also affects education, since we know those things are true. So let me show briefly a picture of what that would look like. It would look like this. So what's happening here is that if we leave parental socioeconomic status out of the model, in other words, its effects are basically included in the error term. And if that were an appropriate assumption, what that would mean is that in some cases, having high parental socioeconomic status would be like associated with having a little bump in your income, and then in some cases it would be associated with having a little dip in your income. It's obviously not very realistic. It's probably, generally speaking, going to result in higher income. If that were the case, then it would be well and truly part of the error term. So we would be correct to include it in that error term. But if it's not just adding random noise, then it shouldn't be. And what's happening then in that situation is that we're going to end up with a case where there is an association in reality between the error term and education. So generally speaking, as education increases, parental socioeconomic status increases, and you're generally speaking going to have a higher income. Now, you can't actually see evidence of that from the actual model because the way that we estimate the regression equation is that we force there to be zero association between the residuals and education. But a lot of times you're able to find indirect evidence for that, and it's also just something to be aware of, that even if you don't have evidence, you should still use your common sense and say, well, that's probably not the case. We don't want parental socioeconomic status to be absorbed into the error term. And in the worst case, you could have an even more kind of obvious problem, which is that what if education is no longer or is conditionally unassociated with income once you control for the effect of parental socioeconomic status? And again, that's something that we don't know until we include those other variables in the regression analysis. I wanted to show you something kind of interesting here. So it turns out that although it's difficult to represent multiple regression either in subject or variable space, once you have a large number of predictors, that you can use what's known as the Frisch-Level theorem, or the regression decomposition theorem, I think it's called in some sources, but I just know it as the Frisch-Level theorem. You can use that to basically show what the effects of multiple regression are using just bivariate regression. So let me show you what that looks like. Here on the left, we've got respondents' education in years as a function of mother's socioeconomic status using GSS data. And you can see that there's clearly a relationship between the two. But then you can include a whole set of controls. And again, I can't show you what that full multiple regression looks like here. But what I can show you is something that turns out to be somewhat strikingly equivalent to that. And what is equivalent to that is this. Taking the residuals of education once we've cleaned all the controls, and then taking those residuals and then regressing them on mother's socioeconomic status cleaned of regression on the controls. So in other words, we strip out the effects of the controls from the outcome and the predictor, And then we just redo the regression. So that ends up being something we can easily understand and picture. And you can see here that there's basically no relationship. So those controls were things like mother's education, father's socioeconomic status. And it basically turns out that there was no longer any association left over between these two things once we do that conditioning. It does look like there's a slight upward slope, but you can actually see that this green error bar that we'll learn to make later in the class basically means that it's not statistically significant. Sometimes there is some indirect graphical evidence that our model is misspecified. So here, for instance, you can see another kind of example of that height-weight relationship from before. And note here that, and this might surprise you at first, there's actually zero relationship between the residuals and the predictor here. And that might seem kind of wacky, because isn't there clearly a nonlinear pattern here? Yes. But this exact regression line is chosen and can be chosen. It can always be chosen, apart from certain exceptional cases that aren't worth going into here, so that the residuals happen to have zero correlation with the predictor. And notice that that does sort of appear to be true. So clearly here the residuals are above the predictor, or the prediction line, which is just a scalar multiple of the predictor, so it comes to the same thing. And here they're below it, and then here they're above it. So it does appear that there maybe isn't any association, right? If we did plot the residuals here, because sometimes they're above it, sometimes they're below it, and then there's a little bit more heterogeneity here. And that actually can produce a situation where there's zero linear relationship between the predictors, or the predictor in this case, and the residual. And that's what's happening here. One way to think about that too is actually to get a deeper picture on what regression is. So regression differs from other procedures, such as a list of conditional means for values of the predictor, in the following way. So regression can weight areas, and in fact it does weight areas where you've got a lot of stacked or dense data. So here we've got a lot of data. Here you can see from the way I colored this, we don't, and then here we've got a lot more data. There's just fewer points here. There's fewer points here. If you did just have a list of conditional means, in other words, you wrote down like the value of the predictor and then the conditional mean of weight there, that actually would show like a very clear relationship, basically. Like it's a one alternative that would not be sensitive to that weighting. But because of that weighting that regression does, and that correlation does, in fact, it means that even though it seems like there's this obviously nonlinear pattern, and maybe even seemingly some kind of a linear pattern, it's because it doesn't actually weight these very heavily in figuring out if there's a correlation between residuals and predictor, that there actually is no pattern here, even though there appears to be. But that doesn't mean that all is well. And that's because there's clearly a nonlinear pattern here. So if we look at this, we see that if we do a nonlinear regression, which is an advanced topic we don't have time for in this class, you can see that the nonlinear regression method very clearly picks up on this nonlinearity, even though the linear regression of the residuals on the predictor, you can see that regression line is flat. It has to be flat. That's the way we choose the regression estimates. It's not a coincidence. I will ask about this on a test because it's really important to understand what regression really is. But there's clearly a nonlinear pattern giving some evidence that we've misspecified our model. Probably what we should do here is go ahead and transform the outcome. And in this case, I took the natural log of weight, and then I took the root of weight, and then I did regular linear regression. And you can see that when we take the natural log of weight and regress it on height, it's actually an extremely good fit. So the r squared is 0.79, which is pretty incredible, which means that the r is actually, I actually can't do that in my head very easily, but it's an extremely high value. It's like in the 0.9. So once you take the natural log of weight and compare it to height, those have an extremely tight relationship. And that's a way to kind of get around that problem. If you did look at the residuals here, there is no nonlinear pattern, and obviously there's no linear pattern by construction. So that is a nice solution. There's a whole lot of other regression diagnostics that can help diagnose all manner of problems. We're not going to get to many of them in this class, but one problem discussed in 361 at length that I mentioned before is heteroscedasticity. I just want to call your attention to that one more time. That's a fancy way of saying that the variance of the residuals is not constant on the value of x. So here you can see there's clearly much more spread in some regions of the graph than there is in others. And this is the, pardon me, regression of the residuals on the predictor. Note that there's something of a nonlinear pattern here. You can see it most clearly here. But the main point is that there's just obviously more spread. This is the residuals on the predictor, but of course it looks very much like the original graph. And what that tells us is that our model just simply isn't that well specified. Finally, you want to be careful with associations between high-level units. This is the last thing I showed in class, so I won't go over the final thing I showed here. But there's this interesting fact that, for instance, the relationship between the income of a state and votes for George Bush in 2004 appeared to be the inverse of what you might expect from kind of basic political science. So it looked like the wealthier a state, the smaller the vote share for Bush, which seemed to turn some conventional wisdom about poorer people and working class people generally voting Democratic on its head. It turns out that this relationship reverses if you look at the income of individuals in the vote share for Bush. And the reason for this is that the income within a state doesn't tell you anything about the income of the people actually voting, for instance. So what does this mean? Well, one way to explain it is that as the income of the state goes up and the vote share for George Bush goes down, what that probably means is that poorer people in, say, high income states like Massachusetts, for instance, are generally turning out at high rates. And again, that's got to be true in some way, or else this can't be true. And you might theorize that maybe there's a strong union presence in these states. In fact, that's true. Maryland, New York, Massachusetts, New Jersey, and Connecticut, all generally speaking, have pretty high union densities. Same with New Hampshire, and then California here. And so even though these are high income states, there are also states that have fairly large union movements. Those movements tend to turn people out to vote. And then conversely, it might be the case that as you go down to these poorer states here, it may be the case that poor people in these places, such as Mississippi, generally speaking, have very low turnout of working class people. So you have really disproportionately large numbers of rich people voting in those states. That's actually a bit of sociology that's kind of interesting and fun, but not directly related to the math. The math takeaway is just beware of this. This is the ecological fallacy, and it embarrasses a lot of people because they don't think about it, and then it turns out that the real stories are often more complicated. Finally, I'm going to omit this here because this is about COVID and is now something that would take a long time to explain. See the comments if you want to know why this is an example of really bad regression. It's kind of an interesting thing to discuss, but I don't have space here. So thanks everyone for watching this video on regression analysis.